universe. We're really reconsidering its very nature piece by cosmic piece. We're looking at a truly radical new theory. Prepare to plunge into the psychedelic superfluid universal morphonic ocean theory, or, well, PSUMO for short.
It's quite a name.
It is. And our mission today is to unpack how recent, really stunning observations from the James Webb Space Telescope are, well, they're not just challenging our existing understanding of the cosmos. They seem to be providing powerful corroboration for this bold new paradigm.
That's the really interesting part, yeah.
Then we'll dive into some mind-bending next-generation predictions from PSUMOT that could be just around the corner. Predictions that, offer concrete, falsifiable ways to actually test this revolutionary idea.
Which is crucial for any scientific theory.
Exactly.
Yeah.
We've gathered insights from several key sources, detailed notes on these predictions, analyses of the latest JWST findings, discussions on some perplexing black hole discoveries.
A lot to cover.
A lot. So if you've ever felt like the universe is more than just disconnected parts, or maybe wondered if there's a deeper, hidden unity beneath it all,
yeah,
this deep dive is definitely for you. Get ready for some serious cosmic perspective recalibration.
Indeed. And what's particularly fascinating here is how the standard model of cosmology, the LambdaCDM model.
The one we've relied on for decades.
Precisely. It's been the bedrock, incredibly successful for a long time, yet under the scrutiny of this new high-fidelity data, especially from JWST, it's really beginning to show significant signs of strain.
Like cracks appearing.
Almost exactly like that, yeah. Hairline cracks in a foundational structure, and PSUMOT rather than just inventing exotic new particles for every little anomaly.
Which seems to happen a lot.
It does. Instead, it offers this unified structural understanding of the cosmos. It pictures the universe as a cosmic quantum superfluid.
Okay.
So the deep dive will, I think, illuminate how these recent findings aren't just highlighting the standard model's limitations, but they're powerfully pushing us towards that structural understanding.
Yeah. Suggesting the answers might be in the structure itself.
Exactly. Suggesting that many of the universe's deepest mysteries might be solved by looking at its inherent fluid-like nature, rather than simply adding more ingredients to the cosmic recipe.
Okay, let's unpack this crisis then. LambdaCDM, our current understanding. It's given us an incredible framework, right? Big Bang, galaxy formation, all that.
Absolutely. Immense explanatory power.
But lately, as you said, it's hitting some serious roadblocks. Our sources use this powerful phrase, calling it a crisis of fragmentation. What exactly is this crisis? Why is it so significant? Is it just one or two tricky observations, or is it something, deeper?
That's a crucial point. It's definitely deeper. The PSUM paper opens by stating that LambdaCDM has entered a period of crisis, strained by persistent observational anomalies.
Persistent.
Yes. And it's truly a crisis of fragmentation, because these aren't just isolated minor issues. We're talking about a growing collection of puzzles that the standard model struggles to explain individually, and maybe more importantly, coherently.
Like they don't fit together.
Precisely. For instance, a prime example everyone talks about is the Hubble tension.
Right, the expansion rate disagreement.
Exactly. Measurements of the universe's expansion rate, the Hubble constant, they vary significantly depending on whether you derive them from the early universe, like using the cosmic microwave background radiation.
Big Bang's afterglow.
Right. Or if you measure it from the late universe using local observations of things like supernovae.
And the numbers just don't match up.
They don't overlap within their error bars anymore. The discrepancy is now statistically significant beyond what chance can explain. It really points to something fundamental being, well, amiss in the model.
And it's not just the Hubble tension, is it?
No, not at all. There are other things, like inconsistencies in how matter seems to be distributed on very large scales, or the missing satellite problem.
Where we don't see as many small galaxies orbiting big ones as the simulations predict.
Exactly that. So these aren't just loose threads anymore. They feel like they're starting to unravel parts of the whole cosmic tapestry woven by LambdaCDM.
So it's not just about individual anomalies, but also about the bigger picture. The inability to connect all the dots, like you said. Pieces of a puzzle that just don't quite form a coherent whole anymore, leading to this failure of synthesis.
Precisely. That's a great way to put it. Beyond individual anomalies, one of the most significant strains is this struggle to coherently explain how different cosmic components, galaxies, stars, black holes, how they co-evolve and interact, especially in the very early universe.
When things were happening really fast.
Extremely fast and under very different conditions. We have these highly refined models for stellar evolution, for galaxy formation, for black hole growth. But connecting them all into a single, seamless, self-consistent narrative, particularly back then, it's become increasingly difficult. This suggests what our sources call that failure of synthesis, a lack of a unified picture where all these elements neatly fit and influence each other dynamically. This fragmentation really hints that we might be missing a more fundamental, underlying principle, something that dictates these interactions across all scales.
And that's where PSUMOT comes in, right? With a totally different way of looking at everything. Instead of seeing disconnected pieces, it proposes this underlying fundamental unity. Can you maybe elaborate on that core idea? What is this cosmic quantum superfluid?
Right. To really visualize this, you need to step away from the traditional picture, vast, empty vacuum with galaxies just scattered within it like islands.
The standard picture.
The standard picture. PSUMOT proposes the universe is fundamentally not empty. Instead, it's a continuous, all-encompassing ocean of quantum fluid. It suggests the universe isn't a void filled with objects, but rather it is a single, coherent quantum system, this cosmic quantum superfluid.
Okay, wow. So everything is part of this fluid.
Think of it like this. Everything we perceive, every particle, every force, even the fabric of space-time itself, isn't a separate fundamental brick. Instead, they're all emergent phenomena.
Emergent, like waves on water.
Exactly like waves or currents or even tiny vortices forming within this single, unified cosmic quantum superfluid. The fluid itself is the primary reality, and everything else is just a manifestation of its dynamics, its behavior.
That's a complete flip.
It's a complete inversion of how we typically understand existence. It replaces a static stage with a vibrant, dynamic medium.
That's a profound shift in perspective. So if the universe is this unified superfluid, how does that help with these cracks we're seeing in the standard model?
Yeah.
Doesn't mean we don't necessarily need to, invent new exotic particles every time something doesn't quite fit. We just need to understand how this fluid behaves.
That's the absolute essence of the structural solution concept, which is key here. PSUMOT posits that many of these cosmological tensions don't actually require entirely new physics in the sense of new fundamental ingredients.
Like inventing WIMPs for dark matter, or some new energy for dark energy.
Exactly. Those are substantive solutions adding new things. PSUMOT suggests the solutions might be found in understanding different processes and dynamics within this superfluid. It addresses what it calls a failure to account for the universe's structure and large-scale dynamics.
So it's about the behavior of the structure, not new components.
Precisely. It's about recognizing that the anomalies we observe aren't flaws in the universe, but rather our own failure to grasp the fundamental fluid-like medium itself, and how excitations and dynamics within it give rise to the phenomena we see. It feels like a much more elegant approach than constantly adding new, unobserved ingredients. It suggests the answers are already there, encoded in the very structure, the very fabric of the cosmos.
What's truly captivating is how recent astronomical observations are, well, quite literally forcing us to reconsider some fundamental assumptions.
Yeah.
The James Webb Space Telescope, JWST. The data it's sending back isn't just new, it's actively contradicting what we thought we knew in some cases.
It really is.
Can you elaborate on what JWST has found that's causing such a stir, especially regarding those early universe black holes? And how does it align so powerfully with PSUMOT's arguments?
Right. The JWST has presented us with a significant cosmic puzzle, specifically concerning the formation of supermassive black holes very early in the universe's history.
Supermassive ones, not just regular ones.
Supermassive ones, yes. And the key issue is they are far too large to have formed so early in the universe's history, according to conventional models. This is a huge challenge because the timescale for their growth just doesn't add up within the standard LambdaCDM framework.
Because JWST can see so far back, right?
Exactly. Its incredible sensitivity lets us peer back to within just a few 100 million years of the Big Bang, and it's revealing a universe already populated with these absolute cosmic behemoths.
Give us some specific examples, because the numbers I've seen are truly mind-boggling for objects that existed when the universe was still basically an infant.
They really are. One remarkable example is a supermassive black hole found in a galaxy called Kuiper's LRDZ9. This black hole is estimated to be somewhere between 38 million and possibly up to a staggering 300 million times the mass of our sun.
300 million?
Yes, and it formed only about 500 million years after the Big Bang.
Wow. That's The universe was what, maybe 3 or 4% of its current age?
Something like that. Tiny fraction. Another amazing discovery highlighted in our sources is an SMBH in what they've nicknamed the Infinity Galaxy. It seems to have formed in a really unusual location, right between two colliding galactic nuclei.
Suggesting the collision itself played a role.
It strongly hints at non-standard mechanisms being at play, suggesting that the environment, the structure of the early universe, was somehow conducive to this incredibly rapid, massive formation. These aren't just one-offs, they're patterns emerging from these early universe observations, signaling a fundamental gap in our understanding.
And the light seed theory is the traditional way we thought black holes grew, wasn't it? They start small, maybe from a collapsed massive star, and then they slowly gather mass, accrete matter, over billions of years. These JWST findings, especially for these early behemoths, must just completely shred that idea.
They absolutely do. The traditional model posits black holes growing slowly from these collapsing stars, forming relatively small light seeds, maybe a few tens of solar masses tops.
Okay.
This process is gradual. It involved these stellar remnants pulling in gas and dust over immense stretches of cosmic time, and it's often limited by something called the Eddington luminosity.
Which sort of puts a speed limit on how fast they can eat.
Exactly. It determines how fast a black hole can accrete without basically blowing away its food source with intense radiation. For a black hole to reach hundreds of millions of solar masses in just 500 million years, it would need to grow at an absolutely impossible rate, continuously accreting matter far, far faster than conventional physics allows.
But the math just doesn't work.
The math just doesn't work. These JWST findings make that light seed model utterly untenable for these early massive objects. The sheer scale and the rapid formation challenge the very foundations of our black hole growth models. They demand an entirely different explanation.
What's truly remarkable here, as you said, is that while PSUMOT didn't explicitly predict these specific discoveries, it didn't name Capers LRDZ9.
No, of course not.
These findings serve as this powerful, almost perfect vindication of its foundational arguments. It's so aligned, our sources suggest it could be retroactively called prediction zero. It's like the universe itself is confirming the cracks that PSUMOT pointed out in the standard model.
Precisely. It's a striking convergence. These discoveries force cosmologists to seriously consider alternative theories, things like the direct collapse of huge primordial gas clouds to form massive seeds.
So it's starting much bigger.
Much, much bigger. Potentially thousands, maybe even hundreds of thousands of solar masses right from the outset, skipping the whole single star collapsing stage entirely. Or, alternatively, scenarios involving rapid growth, where black holes somehow grow at an incredibly accelerated rate in the dense, turbulent, gas-rich conditions of the early universe. The feedstock for growth was just far more abundant, and maybe the accretion process was more violent than we previously imagined.
So a different starting point or a much faster process.
Right. It's a profound shift in understanding how these cosmic giants are born and evolve, moving away from that gradual bottom-up picture to one that's much more immediate, much more forceful.
And this massive seed idea, or these rapid growth scenarios, this is what PSUMOT means by a structural solution, isn't it? It's not about inventing some new particle we haven't found, but about understanding a different process or dynamic within the universe itself, driven by its underlying structure. How is this a structural solution rather than just, a new ingredient?
Absolutely. This shift from the light seed growth model to a heavy seed or rapid growth scenario is a perfect real-world example of what PSUMOT calls a structural solution. It's not about invoking an entirely new, undiscovered particle or a previously unknown fundamental force.
Right.
Instead, it proposes a different process, a different set of dynamics driven by the unique, extreme conditions inherent to the early universe's structure. Things like immense gas compression during galactic collisions or the existence of these vast, unstable, primordial gas clouds. It's about understanding how the environment, the fabric and flow of this cosmic superfluid with its unique energy and density distributions, influences what emerges within it.
The medium dictates the outcome.
Exactly. This directly supports PSUMOT's argument that the answers to these cosmological tensions lie in the universe's interconnected structure and how that structure dictates the dynamics, rather than solely and purely substantive particle-based explanations. It's about the medium, the flow, influencing what comes into being.
So it's not just these early supermassive black holes that are hinting at problems for the standard model. Our sources also mention other black hole anomalies, pointing to its limitations, maybe even closer to home, in a more recent universe. What are these other puzzles?
That's correct. It's not just the early universe. Beyond these early SMBHs, other black hole observations also point towards the Standard Model's limitations, particularly coming from gravitational wave astronomy.
From LEGO and Virgo detections.
Precisely. We've detected black hole mergers involving masses in what's known as the mass gap. This is a range where current stellar evolution models say black holes shouldn't really exist.
Okay, what kind of masses are we talking about?
For example, we're seeing intermediate mass black holes, or IMBHs, with masses around, say, 20 to 30, maybe 30 to 40, 50, or even up to 100 times the mass of our sun.
Right.
According to our standard understanding of stellar evolution, stars heavy enough to form black holes typically either create smaller ones, maybe up to around 15 or 20 solar masses, or, if they're extremely massive, they hit this pair instability supernova phase. This completely blows the star apart, leaving no black hole remnant at all, or they collapse directly into very large black holes, maybe 150 solar masses or more.
So there's supposed to be a gap in between.
There's supposed to be a gap in that intermediate range, but we're seeing mergers in that gap. These observed IMBHs just don't fit neatly into our categories of how stars die and form black holes. It's another puzzle piece that doesn't quite fit.
Right. I remember the buzz around those discoveries. They're too big to be regular stellar black holes, but too small to be the supermassive ones at galactic centers. They just don't fit. And what about their spins? I heard something about that too.
Exactly. And adding to this, some of the detected mergers involve black holes with unusually high spins, sometimes very close to the theoretical maximum limit allowed by physics.
Faster than they should be spinning.
Much faster than expected from standard formation channels. The spin of a black hole is basically a relic of the angular momentum of its parent star and whatever it accreted later. In standard stellar evolution, stars lose a lot of angular momentum through stellar winds. So observing black holes spinning near the theoretical maximum suggests formation pathways or merger dynamics that aren't fully accounted for in our standard models. It hints, again, at a more complex, perhaps environmentally driven process for their formation and evolution, again, pushing us towards a more structural, dynamic understanding rather than just simple stellar collapse.
So, as our sources suggest, this isn't really a problem to be solved with a quick fix, but more like an exciting time on the frontier of science. It shows how new, precise data forces us to fundamentally rethink our assumptions.
Absolutely.
And this really sets the stage perfectly for PSUMOT's more specific next-generation predictions, doesn't it?
It absolutely does. These aren't problems in a negative sense at all. They're opportunities for profound discovery. They clearly indicate that our current models, while successful in many areas, are fundamentally incomplete. They're pushing us to explore new conceptual frameworks like PSUMOT, which offer a potentially more unified explanation. The universe is basically telling us there's much more to the story, and it's doing so with increasingly high-fidelity data.
Okay, so what does this all mean then? If PSUMO is correct, and the universe truly is this cosmic quantum superfluid, what other amazing observable phenomena should we expect to see as our technology keeps advancing? This is where we get into those next-generation predictions, the really exciting, truly mind-bending stuff that could actually confirm this entire paradigm.
Indeed. And these are deeper, subtler signatures of the cosmic superfluid. They go beyond that initial validation we're seeing from the early black holes. They offer, as you said, concrete, falsifiable ways to test the PSUMO paradigm.
Falsifiable is key.
Absolutely. These aren't just theoretical musings. They are specific observational targets that future observatories and experiments could potentially confirm or, importantly, refute. If these predictions hold true, it would fundamentally reshape our understanding of the cosmos, providing direct evidence for this underlying fluid reality.
Okay, let's dive into the first one. Gravitational wave astronomy and something called an effective refractive index for spacetime. Now, we usually think of light bending as it passes through water, right? It slows down, changes direction.
A classic example of refraction.
What if gravity waves, the actual ripples of spacetime, did something similar? That feels...
Well, it fundamentally challenges our centuries-old understanding of space as just a passive, empty void.
That's a perfect analogy to grasp the core concept. In Einstein's general relativity, gravitational waves, GWs, are ripples propagating through a vacuum at the speed of light, c. The vacuum of space is considered just that, empty. It's a passive stage for events, with nothing there to impede or alter the wave's intrinsic speed.
But PSUMOT says no vacuum. But in the PSUMO paradigm, there is no true vacuum. The universe is entirely filled with this cosmic quantum superfluid. And that premise alone has profound and crucially testable consequences for how gravitational waves behave. It means space-time itself is not empty, but a dynamic, interacting medium.
Okay, so if the universe is this pervasive superfluid, how would that actually affect a gravitational wave passing through it? What's the fundamental mechanism at play?
Okay, so as gravitational waves travel, especially through the dense superfluid cores thought to exist in galactic halos.
Where the dark matter is supposed to be concentrated.
Exactly. As they travel through there, they must interact with this medium. Specifically, they would interact with the superfluid's collective phonon excitations.
Phonons.
Yeah,
Okay, what are those again? Like sound particles.
that's a good way to think about them. In a regular fluid, sound waves are just vibrations of molecules, right? But in a quantum superfluid, like the one PSUMOT proposes, these vibrations become quantized units of energy, like particles of sound. They carry information, momentum, even force within the fluid. So when a gravitational wave, which is a ripple in space-time itself, encounters the superfluid, it's not passing through nothing. It's subtly engaging with these phonon excitations. It causes a microscopic disturbance that, over cosmic distances, can accumulate into a measurable effect. This interaction is the key, a subtle coupling between gravity and the fluid medium that influences the wave's journey.
And what would be the observable effect of this interaction? If it's like a refractive index, does that mean the gravitational waves would actually slow down a tiny bit?
Precisely, that's the prediction. This interaction would create an effective refractive index for space-time within the superfluid. This means the propagation speed of gravitational waves would be slightly altered. They would deviate from the speed of light, c, in a way that depends on the density of the superfluid and also the frequency of the gravitational wave itself.
So denser fluid, more slowing.
Generally, yes. In essence, the GWs would experience a subtle drag or resistance as they move through the medium. This shifts space-time from being just a passive stage to being an active participant in cosmic drama. It's a truly profound rethinking of the universe's basic fabric.
Imagine a cosmic race. So how would we actually see this? What kind of multi-messenger observation could confirm this effect for listeners out there? How could we possibly measure such a tiny difference?
Right. The key is multi-messenger events. Think about the merger of two neutron stars. These events are incredible because they produce both a strong gravitational wave signal and a powerful electromagnetic counterpart, like a kilonova, which is a burst of light across different wavelengths.
We detect both signals from the same event.
Exactly. So according to PSUMOT, we would expect a measurable time of arrival delay between the two signals if the path they travel traverses a dense region, like a galactic halo. The gravitational wave signal, being slightly slowed by the superfluid medium, should arrive slightly after its electromagnetic counterpart, the light signal.
Because the light isn't affected in the same way?
Light interacts differently. In this scenario, the GWs are slowed by the superfluid structure itself. This effect would likely be negligible, almost undetectable, in the truly empty voids of intergalactic space where the superfluid density is extremely low.
Okay.
But it should become apparent and measurable for events whose signals pass through dense galactic halos, or maybe for signals that are gravitationally lensed by foreground galaxies, where the path is forced through these denser regions of the superfluid. This would provide a direct probe, a way to measure the density of the superfluid in those regions.
That's an incredible thought, to literally measure the texture of space by timing gravitational waves against light. But given how subtle these effects must be, what are the biggest challenges to actually observing such a tiny time delay? Are we talking decades away, or could current or near-future experiments do this?
That's the critical question, the practicality of it. The challenge lies in the extremely high precision required. Even a tiny deviation from sense translates to a very, very small time delay over cosmic distances. We could be talking about milliseconds, maybe even microseconds, over millions or billions of light years.
Tiny fractions of a second.
Incredibly tiny. So the biggest challenge is instrumental sensitivity and also pinpointing the event's location and timing extremely accurately. We likely need future gravitational wave observatories, perhaps next-generation ground-based detectors that are even more sensitive than LIGO and Virgo, or maybe even space-based interferometers like LISA.
Okay, so maybe not tomorrow, but plausible.
Plausible, yes. These future instruments promise much higher signal-to-noise ratios and the ability to localize GW sources with extreme accuracy. Plus, we need to simultaneously observe and precisely characterize the electromagnetic counterpart to establish that unambiguous start time for the signal race. So yes, it's challenging, but the advancements in both GW and electromagnetic astronomy are definitely bringing this within the realm of possibility, maybe within the next decade or two.
So if the very texture of space can influence gravitational waves, what about the largest, most visually stunning structures in the universe, those immense cosmic superhighways connecting galaxies, the cosmic web? We usually think of them as just scaffolding for dark matter.
Right, a static framework.
But PSUMOT paints a far more dynamic, almost alive picture of these filaments, doesn't it? Like actual conduits.
It absolutely does. The cosmic web, this vast network of filaments connecting clusters of galaxies, is one of the most striking features we see in large-scale structure surveys. In the PSUMOT model, these are not merely static filaments of dark matter serving as a gravitational backbone. They are envisioned as vast, perhaps even spinning conduits of the cosmic superfluid itself.
Spinning? Wow.
Potentially.
Yep.
And as a physical medium, these filaments should be able to transmit disturbances, much like how a hosepipe channels water, or maybe like a fiber optic cable guides light, but on a truly cosmic scale, they become active pathways for energy and information.
So these cosmic superhighways aren't just passive structures, but active pathways. What kind of disturbances are we talking about, and how would they travel along these filaments?
Exactly, active pathways. And the fundamental carriers within this superfluid are those phonons we mentioned, the quantized sound waves.
Oh, okay.
So imagine a really energetic event happening at one node of the cosmic web, maybe where filaments intersect, like a major galaxy cluster merger. That wouldn't just send out gravitational waves in all directions. It would also generate a massive pulse of these phonons within the superfluid.
A sound burst in the superfluid.
A huge sound burst. And critically, these phonons wouldn't just radiate out isotropically, like light or gravitational waves spreading out spherically in a vacuum. Instead, they would be channeled along the superfluid filaments. They'd propagate primarily along these conduits at the medium speed of sound.
Like sound traveling down a pipe.
Exactly. Think of it like a cosmic railway track, guiding these sound waves efficiently across immense distances, following these cosmic superhighways from one galaxy cluster to another.
It sounds like a cosmic ripple effect, but along specific channels. So what would we actually observe if this were happening? This feels like it has the potential to explain some really intriguing cosmic mysteries.
What's fascinating here, the prediction is, we would expect to see correlated activity in galaxy clusters that we know are physically connected by a cosmic filament.
Okay, like what?
Imagine a major merger happening in one galaxy cluster, or perhaps a period of intense starburst activity, or maybe a powerful flare from an active galactic nucleus, AGN, where gas is rapidly falling into the central supermassive black hole.
A big energy release.
A huge energy release. According to PSUMOT, this event could be followed after a predictable time delay which would match the phonon travel time along that specific filament.
Calculated based on the distance and the speed of sound in the superfluid.
Precisely. After that delay, you might see a sudden onset of similar activity, like a burst of star formation, or AGN activity in a connected cluster, potentially hundreds of millions of light years away.
Whoa, that sounds like, well, the source calls it action at a distance.
It would look like action at a distance. An influence propagating through the cosmic web in a way that's completely inexplicable by light speed signals or standard gravitational interactions alone. You might see, say, an X-ray flare in one cluster, and then, maybe millions or tens of millions of years later, a corresponding burst of star formation activity in another galaxy cluster known to be linked by a filament.
That would be incredible evidence.
It would be direct evidence of the fluid nature and the interconnectedness of these cosmic structures. It would reveal a communication channel across the cosmos we never imagined existed.
That's already pretty mind-blowing. The idea that a merger in one part of the universe could trigger activity in a far-away connected galaxy cluster, not through light or standard gravity, but through sound wave. In the cosmic superfluid, it really changes everything we thought about cosmic interactions. But the implications of a superfluid universe go even deeper, right? What about dark matter itself and maybe the boundaries between different cosmic environments?
Indeed. If we connect this back to the bigger picture of dark matter, which is arguably one of the biggest mysteries in cosmology, PSUMOT offers some very specific, very testable predictions about its behavior at different scales. And this brings us to the concept of phase transitions.
Phase transitions, like water turning into ice or steam.
Exactly like that analogy, but applied to the very nature of dark matter itself, depending on its environment.
Okay, so we're talking about phase transitions at the edge of galaxy clusters. Now, our sources mention that PSUMOT explains something called Mundian behavior. That's a modification of gravity, right? Can you quickly refresh us on what MINDI is, and then explain how PSUMOT suggests superfluid dark matter in galaxies behaves differently than in clusters?
Absolutely. It's a really important distinction in the theory. So quickly, MOND stands for modified Newtonian dynamics. It's an alternative hypothesis to dark matter. Instead of assuming there's extra invisible matter providing gravity.
It says gravity itself works differently.
Yes, specifically at very, very low accelerations, like those found in the outer regions of galaxies. MND proposes a change to the law of gravity there, which could explain the observed galactic rotation curves without needing dark matter.
Okay.
Now, what PSUMOT does is quite clever. It aims to provide a physical mechanism for MND. It suggests a MND isn't a fundamental alteration of gravity itself, but rather an emergent property arising from how superfluid dark matter behaves within galaxies.
So dark matter is real in PSUMD, but it's a superfluid, and that's why gravity looks modified.
Precisely. PSUMOT suggests dark matter in the relatively cool, quiet environment of galactic halos behaves as a superfluid. The unique properties of this superfluid state, especially its collective excitations, the phonons, are proposed to mediate an extra force, effectively mimicking Mundian gravity on galactic scales.
Okay, that makes sense. But what about galaxy clusters? Mundane doesn't work as well there, right?
That's the crucial part. In the hotter, much more energetic environments of galaxy clusters, PSUMOT proposes that dark matter exists in a normal, non-superfluid phase. It behaves more like a regular fluid or gas. This naturally explains why MOND seems successful in individual galaxies but struggles in clusters, where observations still indicate a need for extra mass even after applying MOND.
So different phases in different places.
Different phases depending on the temperature and dynamics. And if this is true, it implies there must be a physical phase boundary where a galaxy's cool superfluid halo meets the hot, normal fluid dark matter of the intracluster medium, perhaps as a galaxy falls into a cluster. This isn't just a theoretical line. It should be a real physical transition zone.
So if there's a physical boundary like that, a literal dividing line between two states of dark matter, we should be able to see it somehow, right?
Yeah.
What kind of expected observations would confirm this phase transition? I imagine it would look quite different from what we expect with our current smooth collisionless dark matter models.
Exactly. If dark matter is just a smooth collisionless cloud, as in the standard model, you wouldn't expect sharp boundaries. But if PSUMOT is right, we would expect very distinct visual and measurable signatures at this interface.
Like what?
One key prediction involves gravitational lensing. High-resolution lensing maps, where we use the distortion of background galaxy images to map the mass distribution in the foreground.
Using galaxies as cosmic telescopes.
Exactly. If we make such maps of galaxies falling into clusters, PSUMOT predicts we should see a sharp break or discontinuity in the inferred mass profile right at the edge of the galaxy's halo. This would be a clear deviation from the smooth, gradually decreasing density profiles predicted by standard cold dark matter models. Instead of gently fading out, you'd see an abrupt, almost wall-like change in the lensing signal, marking that phase transition.
A sharp edge in the dark matter distribution. And what about something we could see in X-rays? Galaxy clusters are full of hot gas that emits X-rays, aren't they?
They are indeed. In addition to lensing, we would also expect potential signatures in X-ray observations. The interaction between the infalling galaxy's superfluid halo and the extremely hot intracluster gas at this phase boundary could create distinct features. Things like sharp contact discontinuities or fronts in the X-ray emission from the gas.
Like a weather front, but between dark matter phases and hot gas.
Something like that. These would be regions showing abrupt changes in the temperature or density of the hot gas. They might resemble shock fronts, but their properties could indicate they're caused by the interaction with a distinct dark matter phase boundary, rather than purely by the gas dynamics we usually model. These specific X-ray features would be quite difficult to explain with conventional models alone, offering another stark indicator of two different phases of dark matter interacting.
That makes a lot of sense. a solid, visible line, or at least a sharp transition, where the superfluid dark matter ends, marking a fundamental phase change. Now let's talk about trying to detect dark matter here on Earth, in laboratories. For decades, the hunt has been focused on WIMP's weakly interacting massive particles. Big, heavy particles.
Right, that's been the dominant paradigm.
But PSUMOT has a completely different idea of what dark matter actually is. And it sort of explains why we haven't found any WIMPs yet, doesn't it?
That's exactly right. PSUMOT identifies dark matter particles not as these heavy WIMPs, but as ultralight, axion-like particles.
Axions. Those are hypothetical particles too, right? Very light.
Very light, yes. Axions are hypothetical elementary particles, extremely light and very weakly interacting. They were originally proposed to solve a completely different problem in particle physics related to the strong nuclear force. But their properties also make them excellent dark matter candidates. So, from PS perspective, the consistent failure of decades of experiments to find WIMPs is, well, entirely expected. It suggests we've been looking for the wrong type of particle in the completely wrong mass range using detection methods that weren't sensitive to these ultralight particles.
Like looking for a whale in a desert when you should be looking for plankton in the ocean, as you said.
It's a very good analogy. We were using the wrong nets in the wrong place.
So if the dark matter is ultralight and potentially superfluid, how would we actually hear it or detect it in a lab? What new kinds of experimental approaches would PSU suggest are needed?
Well, perhaps the most direct proof of superfluid dark matter would be detecting its collective excitations, those phonons again, not necessarily the individual particles themselves.
How would that work?
As the Earth moves through the galactic halo, which PSU describes as this vast dark matter superfluid, we should be constantly moving through it, experiencing a superfluid wind. A sufficiently sensitive detector, perhaps one that even uses a laboratory superfluid like liquid helium-4 as a target medium, could potentially detect the phonons generated by this wind interacting with the detector material. It would be like effectively hearing the sound of dark matter as we sweep through it.
Hearing the whisper of the superfluid wind.
Exactly. Imagine an ultra-sensitive quantum microphone tuned to listen for these incredibly faint quantum sound waves propagating through the detector as they're kicked up by the dark matter wind. That would be a truly groundbreaking moment, directly detecting the collective behavior, the vibrations of the cosmic superfluid itself.
That's a fascinating thought, detecting dark matter not as individual particle hits, but as a collective hum, a subtle whisper from the cosmos. What about detecting the actual particles themselves, even if they're ultralight? Is that possible?
Yes, detecting the individual particles is also a goal, though challenging because they're so light and interact so weakly. As we said, experiments designed for heavy WIMPs are poorly optimized for this. WIMP detectors look for relatively large recoil energies when a heavy particle bumps into an atom.
Which these light particles wouldn't cause.
Exactly. They deposit much, much less energy. So PSU suggests the future lies with new technologies. Things like silicon skipper CCDs. These are specialized charge-coupled devices, like in digital cameras, but with extremely low noise capabilities. They are sensitive enough to potentially detect the tiny interactions, the tiny energy deposits from sub-G particles, which is the predicted mass range for PSUMOT's axion-like dark matter.
Sub-G, so much lighter than WIMPs.
Orders of magnitude lighter. And what's really compelling here and mentioned in our sources is the recent pivot we're seeing in the experimental dark matter community. Because of the lack of WIMP detection, many groups are now shifting focus towards searching for lighter dark matter candidates and developing precisely these kinds of ultra-sensitive technologies.
So mainstream science is moving in that direction anyway.
It seems to be converging, perhaps unknowingly, on the type of dark matter and the detection strategies that align remarkably well with PSURT's predictions. It suggests the experimental evidence, or lack thereof, is pushing the field in a direction consistent with this superfluid picture.
That's a pretty strong indirect corroboration, isn't it? The experiments are starting to look for what PSU says should be there, even without explicitly citing the theory. Wow. This theory really pushes the boundaries of our imagination, from gravitational waves bending to hearing dark matter. It's like a completely new cosmic symphony. But what about even grander scales?
Yeah.
Universe-wide coherence. What's the most speculative, yet maybe the most profound, long-term prediction for a truly unified cosmos, according to PSUMOT?
Right. This really takes the core idea to its logical conclusion. It raises the fundamental question. If the universe is fundamentally a single, coherent quantum system, are there echoes of that initial unity still visible today, imprinted on the very largest scales we can observe?
Echoes of quantum coherence.
Exactly. PSMOT's central idea is this single, coherent quantum system. It proposes that the global phase transition that initiated cosmic acceleration, the event that turned on dark energy, imprinted a baseline quantum state across the entire superfluid universe.
Like setting an initial condition everywhere at once.
In a sense, yes. Now, over billions of years, local dynamics, gravity, structure formation, all that would largely randomize structures. But PSMOT suggests a faint memory, a subtle residue of this initial global coherence should persist across the cosmic web, like a universal quantum genetic code or a primordial seed of quantum order laid down everywhere simultaneously.
A fossil record of the universe's initial quantum state. That sounds incredibly difficult to find. How would we ever hope to observe something so subtle and ancient, spanning scales that are, by definition, beyond causal connection in standard cosmology? What's the expected observation for this kind of cosmological coherence?
It would certainly require immense data sets and sophisticated statistical analysis. The prediction is that future all-sky surveys, capable of mapping the positions and properties of billions of galaxies across vast cosmic volumes, might detect statistically significant alignments of galactic spin axes.
Galaxies spinning in preferred directions.
Yes, but over scales too large to be causally connected by standard gravitational theories. For example, the average spin orientation of galaxies in one supercluster might show a faint but statistically non-random correlation with the average spin orientation of galaxies in another supercluster, hundreds of millions, maybe billions of light years away, even if there's no known physical connection like a filament between them.
Wow. Linked across impossible distances.
This a causal alignment, as the source calls it, would be the ultimate proof of the universe's underlying quantum unity. It would be that fossil record of its initial coherent state, fundamentally challenging our standard picture of structure formation, where influences are limited by the speed of light. It suggests the entire cosmic tapestry might still vibrate with an ancient, unified rhythm established at the birth of dark energy.
That's truly mind-bending, galaxies billions of light years apart, subtly aligned because of an ancient quantum memory. Like a cosmic choreographer set their initial dance steps long ago. It's like the universe is singing a grand, unified song. And speaking of echoes, what about this prediction of a secondary baryon acoustic oscillation peak? That sounds like another echo, but maybe of a different universe-shaping cosmic event.
It is, and it's another potentially profound echo written into the large-scale structure of the universe, but related to sound waves, like the original BAO.
Okay, so refresh us quickly. What are the standard BAOs?
Right. In the standard model, baryon acoustic oscillations, or BAOs, are relics of sound waves that propagated through the incredibly hot, dense plasma of the very early universe before it cooled enough for neutral atoms to form. These sound waves traveled outwards from slight overdensities, and when the universe became transparent, they basically froze in place, leaving a characteristic ripple or preferred distance scale in the distribution of matter.
A standard ruler imprinted on the cosmos.
Exactly. We observe this today as a statistical peak in how galaxies cluster together at a specific separation around 500 million light years.
Okay, so what's the secondary peak predicted by PSUMOT?
PSUMOT, as we've discussed, posits that the universe remains a fluid medium capable of transmitting pressure waves, these phonons, even today. It suggests that the global phase transition marking the onset of dark energy, the moment the universe's accelerated expansion really kicked in.
Which PSUMOT links to a phase change in the superfluid.
Exactly. That transition would have been a cosmologically violent event in the context of the superfluid, and this event would have sent a colossal universe-spanning pressure wave of phonons propagating through the entire cosmic superfluid. Imagine a truly universe-sized tsunami of quantum sound, triggered by the birth of dark energy.
Wow, a cosmic tsunami. So what would we actually see from this big freeze event, this birth of dark energy in our galaxy maps today? How would that tsunami leave a mark?
As our galaxy surveys become even larger and more precise, measuring the clustering of matter on ever larger scales, PSUMOT predicts we should find a secondary, much fainter peak in the galaxy correlation function. Let's call it the PSUMOT.
Okay.
This peak would be distinct from the primary BAO peak. It would correspond to a much larger physical scale, representing the characteristic wavelength of that colossal phonon pressure wave generated during the global phase transition when dark energy became dominant.
So a bigger ripple from a later event.
Precisely. It would be a definitive echo of the birth of dark energy, a structural imprint left on the cosmic web by the maturation of the superfluid itself. Finding this secondary peak would provide compelling evidence for the superfluid nature of the universe and this specific transition event, revealing a whole new layer of the universe's acoustic history.
A PSUMOT peak, alongside the familiar BAO peak. A new signature of a universe-altering event, a cosmic timeline written in sound waves. That's astonishing. Now let's zoom back in a bit, maybe closer to home to galactic halos, like the one surrounding our own Milky Way. PSUMOT mentions vortex annihilation events happening within these halos. What does that mean, and how would we possibly observe something potentially so small yet energetic happening within the invisible dark matter halo of our own galaxy?
Right, this brings us to what the source calls the fine structure of galactic halos. While some earlier ideas might have focused on the static effects of superfluid dark matter, PSU emphasizes that a rotating superfluid halo, like our Milky Way's is thought to be, is a profoundly dynamic system.
Not just a smooth, static blob.
Definitely not. Within this dynamic system, it predicts the existence of quantized vortices. These are tiny, thread-like topological defects in the superfluid. Think of them like miniature, incredibly thin whirlpools or tornadoes within the dark matter fluid.
Okay.
And these vortices aren't static either. They can move, tangle up, interact with each other, and, crucially, they can annihilate with corresponding anti-vortices.
Like matter and antimatter.
Very similar analogy. When a vortex meets an anti-vortex, they can annihilate each other, releasing the kinetic energy that was stored in their swirling motion, but releasing it back into the superfluid itself. Imagine tiny quantum strings snapping and releasing their tension in a burst of energy.
So we're talking about little cosmic pops and chirps from these annihilation events echoing through the dark matter halo around us. What kind of signals would they produce that we could actually detect?
Exactly. Pops or chirps is a good way to think about the potential gravitational wave signal. Future, high-cadence gravitational wave observatories, perhaps ones sensitive to higher frequencies than current detectors, could potentially directly detect these transient events happening within galactic halos.
From vortex annihilation.
Yes. These events would generate a characteristic, perhaps very short-lived, pop or chirp in the high-frequency gravitational wave spectrum. This signal would likely be distinct from the waveforms we see from merging black holes or neutron stars, offering a unique fingerprint of these superfluid dynamics occurring right here in our galactic neighborhood. It would be like hearing the direct sound of the invisible dark matter interacting with itself.
And would there be other forms of energy released from these quantum snaps, not just gravitational waves?
Yes, the theory predicts other signatures too. These annihilation events would also release powerful bursts of those phonons, the quantized sound waves within the superfluid. Now, detecting individual phonon bursts across galactic distances might be incredibly difficult, but these phonons would eventually decay and thermalize, basically, spread their energy out. In doing so, they could create tiny, anomalous hotspots in the temperature of the very sparse gas that exists within the Milky Way's halo. Detecting these small, unexpected temperature fluctuations in the halo gas could be another subtle yet potentially measurable indicator of these quantum vortex events happening nearby.
Tiny hot spots in the halo gas. And anything else? Maybe affecting signals passing through the halo.
Yes, one more intriguing possibility involves pulsar timing arrays. These projects monitor the incredibly precise millisecond-accurate signals from pulsars rapidly spinning neutron stars that act like cosmic lighthouses.
Right, their timing is usually incredibly regular.
Exactly. But if those pulsar signals pass through dense regions of our galactic halo on their way to Earth, PSUMOT predicts they might pick up a unique timing noise. This noise wouldn't just be random static, it would exhibit specific statistical characteristics consistent with quantum turbulence. Yes. Caused by the pulsar signal passing through the chaotic tangle of interacting and annihilating vortices within the superfluid halo. Detecting this specific kind of noise pattern in pulsar timing data would reveal the fine-grained, dynamic, even turbulent nature of our galactic halo, again supporting the superfluid picture.
That's a lot of different, quite sophisticated ways to potentially detect these unseen cosmic events right in our backyard. Okay, finally, let's tackle the most speculative, yet maybe the most profound long-term prediction mentioned. Emergent unification, anomalous graviton-photon coupling. This sounds incredibly ambitious, like it could actually bridge the gap and truly unify gravity and light.
This is indeed PSUOT's most long-term and, frankly, most ambitious prediction. It really touches upon the very foundations of physics, the quest for a unified theory. The premise here goes back to that core idea, that all forces and all particles, which we currently describe as fundamental and distinct in the standard model of particle physics, are ultimately emergent excitations of that single underlying superfluid substrate.
Everything comes from the fluid.
Everything arises from the fluid. And if that's true, then fundamental forces that seem utterly distinct to us now, like electromagnetism, the force carried by photons, light, and gravity, carried by hypothetical gravitons, they must share a common origin. And if they share an origin, they should exhibit some form of subtle, unified coupling, especially under extreme conditions.
Meaning, light and gravity aren't just separate fundamental forces, but different expressions, different waves on the same underlying cosmic fluid. That's the ultimate deep dive into the nature of reality.
It really is. It's aiming for that ultimate unification.
So how would we ever see gravity and light interacting in a way that's not predicted by general relativity? GR has been incredibly successful, and it treats them as separate, right? What's the expected observation for this grand unification?
Right. General relativity describes gravity as the curvature of space-time, and light travels along paths in that curved space-time. But there's no direct coupling or interaction between a gravitational wave and a photon in a vacuum in GR. PSUMOT predicts something different might happen in extreme events.
Like what kind of events?
In the most energetic cosmic events imaginable, think the merger of supermassive black holes, which generate immense gravitational waves, or maybe the incredibly violent crust quakes on magnetars, which produce powerful bursts of high-energy gamma rays.
Okay, the most extreme environments.
Exactly. In those environments, next-generation observatories, maybe advanced gravitational wave detectors working in concert with highly sensitive gamma-ray telescopes, might detect a statistically significant anomalous correlation between the emitted gravitational waves and the high-energy photons.
What kind of correlation?
It could manifest, perhaps, as a slight, maybe polarization-dependent change in the timing or the energy of the photons, which is precisely correlated with the phase of the passing gravitational wave. Imagine the light arriving slightly differently depending on whether it hit the peak or the trough of the gravitational wave, in a way GR doesn't predict.
That would be revolutionary.
Absolutely. This kind of effect is not predicted by general relativity. In PSU, however, observing such a correlation would be the first direct evidence of a unified origin for forces. It would reveal gravity and light as different yet fundamentally interconnected expressions of the same underlying cosmic quantum superfluid. It would be, arguably, the ultimate proof of a truly unified cosmos, a revolutionary moment in physics, achieving a goal sought for nearly a century.
Wow. We have covered a truly mind-bending amount of ground in this deep dive, from those earliest supermassive black holes fundamentally challenging our understanding of cosmic dawn,
Which JWST brought into sharp focus.
the gravitational waves potentially getting subtly slowed down by the texture of space, phonon superhighways connecting distant galaxy clusters,
Yeah.
the idea of dark matter undergoing phase transitions,
And leaving signatures in lensing and X-rays.
even galactic spins, hinting at a universal quantum unity across scales we can barely comprehend, and maybe even hearing the sound of dark matter. PSUMOT really does offer a coherent and incredibly exciting new vision of the cosmos, one where everything is fundamentally interconnected through this superfluid medium.
Absolutely. And what's so compelling about all these predictions we've discussed, from the GW delays to the vortex annihilations to the potential graviton-photon coupling, is their inherent falsifiability.
It can be tested.
They can be tested. Each one offers a concrete, measurable way to probe the PSUMOT paradigm. Their confirmation, even just one or two of them, would provide definitive proof, or at least very strong evidence, for PSUMOT's validity. It would truly usher in a new, unified understanding of the cosmos, one where the universe is fundamentally seen as a dynamic, fluid system.
It really feels like a paradigm shift waiting to happen.
It does, and it's a testament to how new data, especially from instruments like JWST and future gravitational wave detectors, continuously refines our understanding, pushing us to reconsider even our most fundamental assumptions about the universe itself.